So I'm looking at the properties of an ellipse, and defined as Lockwood defines it in his book of curves. He defines it in terms of an envelope, taking a point and running another point along the circumference of a circle. The ellipse is the envelope of the perpendiculars to D here. So let me just do that. And there's my envelope. And let me just turn that grey so it's not quite so in our face. Now, I don't want to turn that one grey. Let's get that back to black again. Okay. Now, if we take a second point on the curve, let's do that. And create its perpendicular. And then intersect those two lines. So first of all, we notice that's not actually on the ellipse. However, if we let the line D come closer and closer to E, and in fact, eventually in the limit become the same point, then F gets closer and closer, and the limit becomes so that it lies on the ellipse. So what we're going to do is we're going to use this finite diagram to get some interesting property of the limiting case. So here's the finite diagram. This is just ordinary non-limit ordinary geometry. Let me just draw the line between D and E. And so again, as we pull D closer and closer to E, you'll see that line becomes the tangent in the limit. But just now it's the chord. And as is the chord, we can see this angle here is 90 degrees, and this angle here is 90 degrees. So both D and E lie on the circle whose diameter is CF. So if we chose these 3 points and created the circle through those 3 points, it would also go through D. Again, I'm going to change the color of that so that we don't get too confused. Make that purple. Okay, so these are angles in a circle. So now if I looked at the chord CD, and now I looked at the this angle here, DEF, it would be the same as the angle CFD. So let me just make those colored so that we can keep our eye on them. So this angle I'm going to make green, and this one going to red. So what we've got in the normal sense of the word, in the normal geometry, no limits involved. This green triangle, this green angle is the same as the red angle because they're both chords, they're both angles at the circumference lying on the same chord, CD. Now, as we move D to C, we can see D towards E. We can see that the red triangle is this one. Let's move that D to E more conventionally. So the red triangle is this one, and the green triangle is this one. So that says that this angle, the angle between the tangent and the line joining the focus to the circumference of the circle, is the same as the angle joining the perpendicular line, joining the focus to the point on the ellipse, and the line which is tangential to the ellipse. Let me just look at that in isolation. So let's go back and draw our circle. So I'm going to use this as a way of drawing the ellipse, using a locus rather than an envelope. That's not what I wanted to do, so we'll undo it. First thing, let's specify the radius, radius A, and let's put in our point again. Distance A times E. Now, what I'm going to do is I'm going to draw a line to the circumference of the circle. We're going to make that point parametric location T, and we're going to stick in a tangent. And then let's just, for the sake of it, put a point where the tangent crosses the axis. That just lets me refer to the angle more precisely. I'd like the angle EDC. So there we have it. It's an arctan with E and cos T and so forth. Let's copy that, because we would like now to have the following point, the point where the angle from the focus here is this, where DFC is the same as EDC. And also this angle here is perpendicular. Right. So we'd like this angle here to be the same as this. So copy it and paste the result in. And so now if we take the locus of that point F, so it's a locus rather than an envelope now, as T varies, we'll see we get our ellipse. We can, if we'd like, compute the equation of that ellipse. And that is in fact the same equation as we got for the ellipse defined as an envelope.